Hi guys, all right, well, let's go ahead and get started with chapter one. So, what's chapter one about? Chapter one is about trying to nail down a definition of AI. What is it? What is artificial intelligence? What does that mean? And in addition to that, it's also trying to talk about, you know, uh, a little bit of the history. How did AI develop, right? What's the history of AI? When did it start? What were some of the milestones in the development of artificial intelligence? And as we're going to find out as you read through the chapter, read through the slides of some lecture, is that AI is kind of like this all-encompassing discipline, right? And it borrows from a lot of other disciplines. It stands on the shoulders of giants that came before it. So as it turns out, it borrows a little bit from mathematics, a little bit from engineering, a little bit from philosophy. I mean, there's linguistics. There's all kinds of disciplines that it leverages to make up the study of artificial intelligence. Okay, so chapter talks a little bit about that. Also talks about what some of those individual contributions were, right? What does it mean to be rational? What does it mean to be logical? What does it mean to think, right? So I think you're going to find as the course progresses that artificial intelligence isn't exactly what you think it is, because you have to answer a lot of questions like, what does it even mean to be intelligent? What does mean, right? I mean, what does it mean to exist? I think, therefore I am. So there's a lot of philosophical questions that go into discussing, well, what is artificial intelligence? Because you first have to knock down what intelligence is, right? You have to first pin that down to be able to, write a program that is intelligent, or to come up with an artifact that is intelligent, right? So in this video, we'll start off with section 1.1, which is trying to give you an idea of the difficulty of defining what AI is, and it's going to serve as the foundation for your first homework assignment, right? I mean, for your first, well, I mean, you had the meet and greet, but I mean, your first AI-related homework assignment where you're going to go out and try to find some definitions of AI yourself. Okay, so let's go ahead and get started with this. So AI, human beings, we, as long as humans have been around, since they came out of the trees, right, and started walking upright, tried to understand, how do human beings think, right? What is our intelligence? What does it mean for us to be intelligent? Are we our brains? Is our intelligence part of our body? Is our personality? Is there a spirit? Is there a soul? What does all of this means, right? So human beings want to understand what our intelligence is and how we think, right? And so if we can pin that down, if we can understand what it is to think, what it is to be intelligent, then when we talk about in the context of artificial intelligence, AI, now what we're trying to do is take that a step further. If we can understand what it is to be intelligent, then we are going to try to build intelligence, right? We're going to try to engineer intelligence. We're going to try to come up with machines that can think, right? But first, we have to understand, how do things think, right? What does it mean to be intelligent? Okay, so section 1.1, what is AI? All right, so the textbook lays out for us 4 different approaches, overviews, right? Trying to understand AI. And there have been different schools of thought as to what it means to be intelligent, or for a machine to be able to think, right? For there to be artificial intelligence. What does it mean? There's different schools of thought on that, right? And so this slide right here kind of summarizes them. The 4 things, 4 different points of view. A machine is intelligent if it can think humanly, right? So here's some quotes. The exciting new effort to make computers think, machines with minds in the full and literal sense, right? Machines that think like human beings. Another quote, the automation of activities that we associate with human thinking, activities such as decision making, problem solving, learning. So one point of view is to say, well, AI, for something to be artificially intelligent, it means that a machine can think like a human being, right? Now, another point of view is that something is artificially intelligent if it thinks rationally. Rationally, right? So, a couple of quotes here. The study of mental faculties through the use of computational models, right? So, how do things behave rationally? The study of the computations that make it possible to perceive, reason, and act. Perceive, reason, and act. Perceive, reason, and act. We're going to come back to that throughout the course. You perceive something, you think about it, you make a decision as to what the best action is, and then you act. Acting humanly. Something is artificially intelligent if it can act humanly. That's another point of view, another approach to understanding what it means to be artificially intelligent. So some quotes. The art of creating machines that perform functions that require intelligence when performed by people. Or the study of how to make computers do things at which, at the moment, people are better. Okay? And the fourth approach, overview, that the textbook brings up, acting rationally, right? So thinking rationally, then there's acting rationally. There's thinking like a human, but then there's acting like a human, right? Thinking, how you think, how you act, not necessarily the same thing, right? So acting rationally. Computational intelligence is the study of the design of intelligent agents. There's that term agent, right? We're going to come back to that. Another quote, AI is concerned with intelligent behavior in artifacts, right? What's an artifact? A robot, right? A self-driving car. Those are examples of artifacts. Okay, so acting humanly. Let's talk a little bit more about that. So maybe you've heard of this before, the Turing Test, right? So Alan Turing, famous computer scientist, mathematician, etc. Really, I mean, you can make the argument that if there was one person during World War II who helped the Allies to win World War II, it would have been this guy, right? He's a major hero. I encourage you to read up on him if you haven't already. His contributions to computer science and the Allied war effort, I mean, they were legion. But anyway, so what's the Turing test? It tries to define intelligence. Okay, so Alan Turing came up with this test and said, look, a computer passes my test, the Turing test, passes this test if a human cannot tell from written responses whether the responder is a computer or a person. Okay, so, I sit down and I write down a question, right? And I hand that to you, and then you go off and you feed it to a computer, right? So I'm separate from the computer, so that way there's no pre-built biases. I don't know. I can't tell just by looking that it's a computer that I'm talking to, right? So I write down a question, I hand it to you, you go and input it in the computer produces some kind of response, you come back and read it to me, or you hand it to me and I read it. If I can't tell the difference, if I can't tell by reading that response that came from a human or from a machine, then that machine passes the Turing test. I can't tell if it's a computer or a person by its response. Okay? Now, one of the great contributions of this of Turing's test is that it helped to define key capabilities that a computer would have to have, that an AI would have to have in order for it to be successful, in order for it to be considered intelligent, right? So in order to pass the test, a computer requires these four things. What? Natural language processing. Because if I write down a question and you have to go input that in the computer has to be able to pull apart, has to be able to communicate in English, has to be able to read my question, okay? Has to be able to perform knowledge representation, right? It has to be able to store what it learns, what it knows about the world, right? So that way it can, in this example, answer the question. Automated reasoning, right? So the machine has to be able to reason out its response, has to be able to think about the question, has to be able to intelligently apply the stored knowledge that it has to answer those questions. Okay, and then finally, machine learning, right? So with machine learning, the machine has to be able to adapt to changes, right? Has to be able to consider patterns, has to be able to think about, how things are related to each other in order to help answer these questions, right? And so Turing framed his question in such a way as to have it revolve around written questions, because intelligence doesn't require physical interaction, right? If I'm talking to you on the telephone, for example, right, you don't need to see my face to know if through our conversation that I'm intelligent or not. You can get a pretty good sense of how intelligent I am just from our conversation, okay? Now, the total Turing test, though, takes that a step further. They say, okay, fine. That's the test is, as it stands, is fine on its own. But if you take it a step further, okay, then you add to the test video and the ability for the machine to manipulate stuff, right? So, you can, the total Turing test, we're like, hey, let's make this test a little bit harder. Let's have a stricter definition. And what this stricter definition does is it brings into the conversation, the need, or that the computer additionally would need, computer vision to perceive objects, right? So, maybe, how many fingers am I holding up? And so the computer has to be able to perceive how many fingers I'm holding up, and then understand through natural language processing what I'm saying, and be able to say, well, you got 3 fingers holding up, or whatever. Robotics, to manipulate objects, maybe, I ask the computer, hey, count out 3 objects from this pile or something, right? And so in order for it to be intelligent, it'll have to grab the 3 objects, right? So the total Turing test, I don't know, maybe gives a more complete picture, right? It's definitely a more strict, involved test. And that test basically defines, like I said, these 6 fields that really allow us to have a conversation about what computers need to be able to do in order for us to consider them as intelligent. Okay, so talk a little bit about thinking humanly, right? So psychology, the study of psychology, you're like, oh, psychology, what the heck does psychology have to do with artificial intelligence? Well, the field of psychology, AI borrows from it, because psychology helps us to understand how we think, how the human mind works, right? So if you're going to build a machine that thinks like a human, well, then you better understand how humans think, because you're not going to be able to write a program based on how humans think if you don't understand how humans think, right? Always remember, step 1, understand the problem, okay? And part of understanding the problem in this case would be, well, how do humans think? Right? So then you can come up with with algorithms, with designs to make a machine that you hope thinks humanly. So what are some tools of the psychologist, right, to try to figure out how humans think? Well, introspection, how do I think about things? You can ask yourself questions. Psychological experiments, Skinner boxes. Well, I say Skinner boxes, but, experiment, that's more for how animals behave. Seeing how people reason, doing experiments, how they react to certain stimuli, that sort of thing. And by asking people questions, if you use brain imaging, you can find out how there are physiological responses, or you can find out how the brain, by what parts of the brain's lights up and stuff, how brain works, what part of the brain is involved in dreaming or reasoning or whatnot. Okay, so once you have a theory of the mind in place, right? Once you think that you understand how the mind works, or you have a theory of it. Now remember what a theory is, right? A theory is not a hypothesis. Theory is, a set of facts, data, a description that says how something works, right? To the best of our knowledge, it explains. It's the highest form of scientific certainty, I guess you could say, right? That tries to explain, according to our best knowledge, how something works. Now, once you have a theory of the mind in place, once you've figured out, well, we think this is how the human mind works, then that theory can be implemented, right? using a computer program. Once you have that theory, once you have an understanding that you think of how the human mind works, well, then you can come up with a plan to write a computer program to mimic that. Okay, so how can you evaluate how good your algorithm is, or how good your plan is, or how good your program was? Well, if the computer's input-output behavior matches human behavior, then pretty good indication, right? Now, the field of cognitive science tries to combine AI computer modeling and psychology into one discipline. And by doing that, they're hoping to come up with falsifiable theories of human minds, how human minds work, right? So what's falsifiable mean? It means that you can prove it to be false, right? If something's not falsifiable, then science can't answer the truth about it, right? Can't prove one way or the other whether or not something works. All right, so thinking rationally. Okay, so the ability for a machine to think rationally. So in artificial intelligence, that's borrowing a lot, right, from Aristotle's right thinking. So the Greek philosophers, hundreds and hundreds and hundreds of years ago, they sat down and said, okay, what does it mean to be rational? How does logic work? What are the foundational rules of logic and reasoning? And so Aristotle, one of the, I guess you could say, founding fathers of rational thought, he came up with syllogisms. He said, okay, if you're going to make an argument, if you want to prove something, and it's going to be correct, then you have to structure your argument in a certain way. Okay, and if it's structured in a certain way, and each one of the facts that you present in your argument, each one of the premises is correct, that is going to inevitably lead to a proper conclusion, which that conclusion is going to be some statement about the world. And so you've proved your case, right? So he came up with these structures for arguments, these syllogisms that are patterns for correct reasoning, okay? And so this provided the foundations for the study of the field called logic, okay, or the study of logic, or this study led to the field called logic, okay? Now, logicians really contributed, or another way that they contributed is they came up with very precise notation to describe reasoning, to describe these forms. It's almost kind of like a mathematical language, and you're going to get exposure to that in this course. You're going to have to go through and do some proofs and a little bit of light, logical thinking, I guess you could say, because you're going to have to play around with first order logic, for example. We'll get there. All right. Now, theoretically, that notation gives us the framework, gives us the tools, okay? Gives us the ability to solve any logical problem, any problem that requires logic, okay? So theoretically, with these tools, we could write a computer program that can solve any problem related to logic, theoretically, okay? Practically speaking, no. Okay, for really complex logical problems, the computational power, the processing to solve these problems, the processing required is huge, right? There may not be enough computational power, processing power on the planet to solve some of these problems. So just because you could solve something theoretically, you have the tools in terms of logic notation, the syllogisms, a framework, doesn't mean that you can write a computer program to do it. Because in practice, you may not have enough memory, you may not have enough CPU power, etc. Right? Some problems are intractable, right? Maybe in other courses, remember talking about certain problems that are NP complete or NP hard or whatever, right? There are limits, okay? How about acting rationally, right? Now, this brings us to one of our first major definitions, which are really, really important, right? So definitions that we're looking at here are the definition of an agent and a rational agent, okay? And this course is focusing on building rational agents, okay? So an agent is just something that acts, right? You're an agent. right? If you're driving your car, you're an agent. If you're walking down the street, you're an agent. You are something that acts. Okay, a Roomba can be an agent. A enemy in some first-person shooter that's controlled by the computer, that's an agent. It's something that is acting within its environment. Okay, now a rational agent. Okay, there's a difference between an agent and a rational agent. Okay, an agent, just a regular agent could flip a coin and decide I'm going to go left or I'm going to go right, or could just roll a die and say I'm going to go down that hallway or something like that. It could be purely random, right? That's not really rational if you're trying to get it to perform a certain outcome. It's going to make irrational decisions, right? So an agent on itself, it just acts, but we're not saying anything about what's motivating its actions. Now, when we talk about a rational agent, what we're saying there is that a rational agent is an agent that is trying to achieve the best outcome or the best expected outcome. Okay, sometimes those aren't necessarily the same thing. We'll talk more about that later, right? But a rational agent is trying to do the best that it can. It's trying to get the best possible outcome. Okay, if you had an agent, say like a self-driving car, and it wasn't acting rationally, you just turned it on and just started driving in random directions, bad, right? Might mow down a bunch of people, might drive off a bridge and kill the passengers or something, right? It's just acting. A rational agent is trying to achieve the best outcome and has a goal in mind, right? Drive from here to San Francisco safely, for example, right? Now it's trying to achieve the best outcome. It may not achieve it, right? Some other car might come along and T-bone it, right? It might smash into it before the car can respond, right? Doesn't mean it's irrational, right? Maybe it tried to avoid the accident, but it was just physically impossible because of the conditions on the road or something, right? But it was still trying to achieve the best outcome of delivering the passenger safely without any accidents or whatever to the correct locations. Okay, so rational agents, they're trying to get the best outcome, and there's going to be inference that is involved there. And again, but sometimes it's not always possible to find the right thing to do, right? So a rational agent has to perceive its environment, has to infer, has to make a decision about what the right best thing is to do. Turn left, turn right, go straight. But it's not always possible, right? Because like that car comes out of nowhere and T-bones your self-driving car, right? It wasn't possible for it to avoid that collision, even though it would have tried to if it could have, right? So all of the skills needed by the Turing test, all of those four things that we laid out, and heck, even with the total Turing test, right? You can even take a step further if we're talking about a self-driving car, right? All of those skills allow for an agent to act rationally. So if an agent can possess or exercise those skills, then it can act rationally. Okay. Again, but acting or perfect rationality, not always possible. It can be very computationally intense, right? Having a self-driving car that's operating in the real world, you can't be aware of everything that's happening in the world all the time. It's just it's just too hard to simulate reality like that. Okay, imagine trying to write a computer program running on a machine that tries to simulate 7.7 billion human beings all acting in a certain way, all the billions of animals on the planet, to try to take into consideration all of their motivations, all the potential actions they could take, so that way the car could behave perfectly in every single scenario. No way. Right? There's not enough atoms in the universe to build a machine that can handle that. Okay. All right. So that brings section 1.1 to a close. In the next video, we'll follow up with section 1.2. If you have any questions, you know how to get a hold of me. Shoot me an email, and I'll stop by my online office hours. Okay. Great. We'll see you next time.